So we'll start at 10, and the topic today will be PyTorch basics. If you already know about PyTorch, Autograd, how to use the optimizer, you can skip this tutorial. But if you stay, I don't want you to stay throughout the tutorial. Okay, you have 3 minutes to decide. Yeah. It's 10 now, let's start. So the tutorial today will be about PyTorch, which is a very powerful deep learning framework that we use, especially in research area. So we can first go to the website, pytorch.org. We will see that it tells you what PyTorch can do, the documentations, the news, etc. We can install it based on like the version. Usually we choose a stable one, and based on your operating systems, like is it Linux, Mac, or Windows, based on your needs. And you can install, usually use pip or conda. If you don't know what's conda and pip, that's an environment management tool. You can use it to like install and manage your environment so you don't have conflicts among different packages. I can tell you more offline. So assume we have pip, then language, this supports Python or C++, and Java. We will use Python here. And the next thing is about if you have GPU on your like laptop, desktop, or server, then it will accelerate your computation by the feature of a GPU computation. And if you do not have one, just choose CPU here. It's much slower, but it's still working. Then it will generate a command for you. You can copy, and then go to your command or terminal or shell, depending on how it's called. Then you press enter, it will start installing for you, but it takes some time. Oh, I already have it, so I'll just use it from my laptop. So now assume I have it. Let's start doing it. The agenda will be like 4 parts, tensor operations, and introduce what's tensor as well. There's 5 minutes about it. Then 10 minutes about Autograd, which means automatic differentiation, a very important concept or tool about PyTorch. And then how can we optimize the function with gradient descent based on Autograd with examples, with like very simple quadratic function to walk you through that example. And lastly, how can we build a like machine learning model to achieve a binary classification problem? Okay, so without further ado, let's start. First of all, we need to import a few like libraries. So we import Torch, which is the PyTorch we just installed, and another like PyTorch.nn means neural network because there are some functionality we need to use, and Torch.optim, which is the optimizer that is already in the Torch as well. For example, SGD Adam, if it's not covered in the lecture to cover later. Anyways, there are some optimizer we can use off the shelf. Then NumPy we talked about in last tutorial and plot for some plot tools. So starting from the part one, how can we do the tensor operations? How can we create a tensor? So we can create a tensor from a Python list. Assume we have a Python list with 3 elements, 1 to 3, then we can just create a tensor with a torch.tensor and then feed the list to it. And we run it, we'll get a tensor 1 to 3. Yeah, very simple. Alternatively, we can also create a tensor from NumPy array. Say we first we have a list, we can convert it to NumPy array y, then we can use torch dot from NumPy to get a tensor y as well. And if you see the difference between x and y, although they came from like almost the same data 1 to 3, their data type is kind of different because x and y they're different in the data type. Here is a torch float 64. It means the precision is different. Here float 64 has higher precision, and actually that will cause some error later if you don't be consistent when like adding different data types together. I'll show you later. So we can do add, which is pretty simple, just like normal Python operation, x plus y. Then you'll get some new number here. Yeah, 264. And we can also do element-wise multiplication. We'll get 1, 4, and 9. Now the thing become we need to be careful when we do dot product, torch dot product between x and y. It will throw error if x and y is not in the same data type, because the error shows us the dot is expecting both vectors here, x and y, to be the same data type, but we found x to be float and y to be double. It means it's not consistent. So we need to convert them to the same data type by doing x.to, which is also a command which is quite useful. Convert to the data type of y data type. So we now, if we check x data type, will be float 64 as well, which is the same as y right now. Now, if we run it, we'll see that we get the result of 14, which is the dot product of x and y. Am I going too fast? Or any question? Yes. It'll be uploaded after the tutorial because I need to like make some last minute changes to that. Yeah. Okay. Any other questions? Okay, if no, let's go forwards. So dot product can also be represented as the add operator, which is the same as the NumPy array. Yeah. Okay. Then I'll skip this stuff because that's almost the same as the NumPy. Like how can you do transpose? How can you do the average over some axis, summation over some axis, which is the same as NumPy, right? So the part two will be interesting part, the automatic differentiation. So we start with the example of a y equals x squared. And we start by one, this is y equals. And we know for this function, the derivative is 2x. And can PyTorch give us this answer? Let's try it with the example here. So say in the code, we initialize x to be 1. And we also need to set, do we need the gradients? Do we require the gradients? Yes, we set it to be true. Otherwise, the PyTorch will not track the gradients of the variable x here to save the computation, to save the memory, etc. And now, first of all, we need to check whether the gradient already exists. If the gradient is not none, it means it's computed before, right? We need to set it to 0. We don't want the gradient to affect us. Now, if we calculate the y, which is x squared, what we need to do is use y dot backward. And this is the template to do the gradients using PyTorch backwards. It means now we need to propagate the gradient backwards. So now after we propagate the gradient backwards, we can calculate the or fetch the gradient of x. Then we will see that the result is 2. The gradient is 2. So it's exactly when we plug in x to be 1 to here, we'll get dy over dx is 2. So this basically means x is here. Then the slope of this tangential line is 2. The slope is 2. And you may wonder why we get only 2 here, not 2x. Because PyTorch only computes the gradients numerically. So there are 2 different types of tools for computing the gradients. The one is called symbolic, and the other is called numeric. So PyTorch is under the category of numerical. And there are other other deep learning framework, which is also numerical, TensorFlow. Not covered in this tutorial, but you'll hear this term very often if you working in AI community. And now what about symbolic? So there are a very powerful tool. Actually, it can do both. So I'll write in the middle. So Mathematica is one of the tools that can do both symbolic and numerical gradients. And the other is MATLAB. Yeah. Can you name a third one for both of them? Sorry? Keras, I'm not sure. Keras is a very high-level API for TensorFlow. Does it support symbolic now? Okay, yeah. Anyways, I think there's something called in Python. There's also a library as well. Anyways, we focus on PyTorch, which only give us numerical results instead of symbolic way. Yeah. Okay, so when I say symbolic, it means the derivative here is represented as still some function, maybe g of x. For example, here will be 2x. But for numerical, we can only get the derivative at some points, which will give us some number here. That's the difference. Okay, so any questions for the Autograd? If no, let's go forward. So the PyTorch, we should start from a simple example. What if our function is nested? Nested means it has multiple steps. We calculated y equal to x squared. Now, what if we also calculate y equal to x squared? That's the first step. Now, second step is if d is x plus y. What's the derivative of d over x? It's just two parts, right? The first part is 1, the second part is 2x. Works like this. And in PyTorch, luckily, we can also do step by step. This may be too simple, too trivial to say, why don't we just combine these two together? Now, I want to say that if it's neural networks, then the function is much more complicated by just simply adding them together. It could be like the first function applies on the input data, right? And after that, we have a activate function sigmoid, and after that, we have another layer of neural net of layer units, and then another activation function, and maybe more layers, right? Then it will be very complicated. We can't just write out the expression in one time. But luckily, we can compute first the fx, then sigma over it, then f over it, then sigma again, then f again. That's just neural networks. So for this, we can get the gradients and add some number, right? Let's see how PyTorch does this multiple steps. So say we have a x still at 1 with a gradient to be 2, and then we calculate y to be x squared, and we want to keep the gradient of y, just some operations. Then z to be the x plus y. Remember, we need to do backpropagate the gradient, so we use z dot backwards. Now, if we check what is the gradient of dy over dz over dx, it will be 3. Why it's 3? Because x is 1, right? So it's 1 plus 2 is 3. It's as simple as that. Now, what about dz over dy? It will be just 1. Because z and y, they're just linear, right? It's 1. It will always be 1, no matter what y value is. So if we check this cell 16, it will be 1. it's consistent with our analysis here, right? So any questions so far? Let me give you one more example. One more example of calculating the gradient for multivariables. Say we have a function y equals 2x0 plus 3x1 squared. Let me write it. Y is 2x0 plus 3x1 squared. And y is a function, it's a function of x0 and x1. Now, if you want to calculate the gradient, we do calculate gradient with respect to each variable here, right? So the gradient, which is a vector here of the partial derivative of y over x0 and partial derivative of y over x1. What is partial derivative of y over x0? Yeah, it's 2. It's a constant, 2. Here, that's 2. What about partial y over x1? 6x1, yeah, 6x1. Okay. So this is the analytical solution, or we say symbolic, right? Symbolic solution of the gradients. Now, what about PyTorch? The numerical answer. If we start x at 1 and 1, and we calculate y written as 2x0 plus 3 times x1 squared, and then we back propagate the gradients, then we print the x grad, it will be 2 and 6. Why is 2 and 6? Because x1 is 1 as well, which will give us 2 and 6. Right, that's consistent. So far we have covered how to use PyTorch to calculate the gradient for single variable function and multi-variable function. And why calculating gradient is useful. So I guess Professor already covered that we use gradient descent to optimize a function, and the gradient is important. That's why we need PyTorch help us to get the gradients. And in neural networks, the parameter is not just 2 variables now. It could be thousands or millions, and maybe ChatGPT is like 70 billion or more, which is impossible for us to write the equation down, like what's the gradient for that function. Yeah. Okay, so I'm going to the part 4 to optimize a squared function, which is basically like the combination of what we talked about previously. So assume we have a function, I call it dummy loss function. It's a quadratic SO, which is x0 minus 3 squared plus x1 minus 5 squared, which is right here. Found to be x0 minus 3 squared x1 minus 5. So if we assume x1, x2, they're all in the range of real numbers. What is the minimizer of this function here? 3 and 5, yes, because it's square, which is set them to be 0. So we know the minimizer will be 3, 5, or maybe I write in vector form. Will be 3 and 5. See if PyTorch can get us there. say we starting from some point 1 and 1. It doesn't matter, just starting from some random points and then see if we can reach 3 and 5, the minimizer. And now we can do one step, which is not enough. Let's see this scary part of the code. Let's break it down. And yeah, we initialize the x and setting the learning rate, which is how much we update towards the gradients, and how many times we update, which is 30, and we record the loss value for later plotting. And then we perform gradient descents over the number of 30 times here. So first we calculate the loss function, then we do the back propagation, and then we update the x value. And yeah, let me explain a little bit. So x minus equal, which is a shorthand for writing x equals x minus the learning rate, I'll say alpha times the gradients, which is a vector. So x actually is a vector as well. Yeah. So this line here, I highlighted, updates the x. And then the next line just reset the gradient to be 0 because PyTorch does not automatically set it to be 0. We don't want the gradient to accumulate, right? When we update this x value, we don't want to keep it anymore. We wanted to reset it to 0 because in the next iteration, we will use new gradients, not the old one, not the or accumulate them together. No. Here is another looks like magic with torch no grad. What does it mean is that when we update the value of x, we don't want to track the trace of the gradients where it comes from. So we just set it to no gradients. And if we keep it, it may throw error or slow down the code. So that's why we don't keep it. Yeah. And then we record the loss value for later plots. So this is one iteration. For the next round, it just calculate the loss with new x here because the x already been updated with gradient descent, right? With the line here from previous iteration. So we calculate the new gradients and then update x with new gradients, then record the loss over and over again. Now let's see what it looks like. So we see that the loss versus the epoch, we see that it's decreasing over time. And at the end, what about the value? We see that the x at the end is 2.9975 and 4.995, which is very close to the analytical solution 3 and 5 we have here. And why it's not close or not exact value? Because I think Professor covered that as well. The learning rate actually affects the accuracy of the gradient descent because yeah, we can use this example, although it's not exactly the same function. So if our learning rate is too large, so starting from here, we need to decrease, right? Decrease x value is x equals x minus alpha times the gradient. And for here, gradient is positive. If alpha is too large, it will make x decrease too much. It may decrease to somewhere here, then it's bad because the loss now is larger. Now, maybe if the alpha is kind of small, it will reach here. And then next step, it maybe reach somewhere here. So depending on the shape, it may reach to the to the minimizer we want, or it may be some oscillation around it because the learning rate is not small enough. Yeah. Anyways, it's a parameter, hyperparameter we need to tune, we need to play with to get us the best loss. Okay, so we covered this. The analytical solution is what we want. Any questions for this part? So if no, we can show another way to do the optimization using the PyTorch optimizer off the shelf instead of we writing the logic. Remember, when we write the logic is the highlighted parts, how we update the X with gradient descent. Now, if in PyTorch, we can use the optimizer off the shelf. So everything before is the same. Now we can use torch.optimizer.sgd means stochastic gradient descent. It's just gradient descent with one single data point. And we can specify the learning rate here. And then what we do is first we clear the gradient from before, right? You just optimizer dot zero grad, then calculate the loss, then backpropagate the gradients, then apply the optimizer. I think this will be in your assignments for how to do the optimization using PyTorch, or later in your project. This is a very templated code for updating your model. Then we record the loss value, and the following is just plotting. And let's see, it gets us the same curve and the same solution near the analytical solution. Yeah. So it's just replacing the logic of updating the model with SGD optimizer here off the shelf. Yeah. And by the way, the X here is the parameter we want to optimize. And for neural networks, it will be the neural network parameter here, what we put here. Okay. So now part for the last part, we want to do binary classification using neural networks. So first of all, we will fabricate, like we make some fake data for us to play with. These toy data sets, maybe not existing in real world. So the task is we need to find a classifier that classify that there are two groups of data, that the data label in green, sorry, not green, blue, and the other in red. Okay, that's the task. There's a problem definition here. Now we need to build the classifier model, and also there's something new came up, new concepts as well. Remember last time we talked about how to write a Python class and how can we do attributes, etc., and inheritance, right? So for class, I'll name it binary classifier, and we need to inherit the PyTorch neural network dot module. So this is the standard way to write a neural network. So what's inside the neural network module is it has some neural network related like package library, and if we inherit it, then this new class I wrote will have all the methods, all the attributes have in this new class. So basically it means it saves us time when we write our own neural networks. Then in the initialization function, we can specify like the input dimension, hidden layer, and output, etc. It's not limited to these three values. It could be more. depending on your needs. Like you can have deeper neural networks, then your hidden dimension will be 3, 5, and like as a list, etc. And we need to write this line for inheritance. So this is also a standard way to write. It's a template. Now for fully connect layer, we have two fully connect layer from inputs from the shape of state 2 to hidden layer 3. And the second layer is from 3 to the output dimension. So if we draw the diagram here, it will be there'll be two inputs, say x1, x2. And in the hidden layer, it has 3 units. And the output is just one value. So network looks like this. Here it's input layer, and here's hidden layer, and here it's output layer. And when we create the fully connected layer, we can use the NN neural network dot linear, which is from the PyTorch. And the first number is input dimension, the second number is the output dimension. So for the first layer, the input dimension will be 2, and the relative output will be here, right? Will be 3. And now for the second layer, here 3 is the input, and here is the output. It's relatively the position. Now the forward function here, which is also a template, we need to write as forward. We can't write as other name like prediction. No, it has to be forward because this is to override the forward method in the class here we inherited. So in this forward function, we write how we compute the forward path from input layer to hidden layer to output layer. Yeah. Like y maybe by hat for prediction value. So how we do it is we first compute the linear operation, right? Self layer over x. So self layer is defined here. And then apply a hyperbolic tangent over it to get y1. And then for y1, we go to the next line. Y1 is fed into the second fully connect layer, and then apply sigmoid activation, then outputs the predicted value here. So any questions so far? I know there's a lot of content if you're the first time writing PyTorch class. So let me wrap here is that when we write it, we need to inherit this module, and in the forward function, we write our logic of doing feed forward computation. So I'll skip this part, okay, let's cover it. It's not that terrifying. So here, it's the same thing. We can actually write our model like this in the initialization. The neural network from PyTorch has a very nice tool we can use is end-of-sequential, means we can build the neural network sequentially. It means just apply layer by layer. sequentially. So we can build a linear layer first, so then build a tangent H activity function. After that, the second hidden layer, and then the sigmoid. We can name it self.model, and then in the forward function, name is very short, just self.model. These two writing, they're equivalents. They're the same thing, just different writing. Yeah, up to your choice. And we can now see what's inside the class. Say we initialize a class and check the parameter. We'll see that the parameter now, the first one is 3 by 2. So 3 by 2 corresponds to here, right? It's 2 by 3. It's transpose. And here is a 3 value here, which is the bias. So here is W1, and B1 is just maybe 1 by 3 or 3 by 1. Anyway, just 3 value here. Then the next is 3 value again, but it has 2 square brackets, means it's actually 2-dimensional. So from here to here, the W2 is 1 by 3, and B2, I think just one number. Yeah, so B2 here just one number. And the number you see here, you see they're randomly initialized. They're not initialized at 0 because it's usually not a good starting point. And you also see that they all have the required gradient to be 2 because they are all the parameters we want to optimize. We want them to have the gradient to be computed. So they all have the gradient requires gradient to be set to 2. Okay. So now finally, let's put everything together to have the training pipeline. First of all, we create data set of 500 points where X is the coordinates and Y is the label. Is it blue? Is it blue or is it red? And then we create the model instance, and using the binary cross entropy loss. Is it covered by the professor yet? No? Okay, anyways, it's a loss to classify for classification problem. Let me Google that first to make sure. So binary cross entropy loss. Yeah, it's this one. So it's y times y times log y hat plus 1 minus y of 1 minus y hat. Right? Okay. So this is the loss function. We want to minimize this loss for having the correct classification. And how does that work? So y is the true label. While y hat is the predicted label. And y is the value of either 0 or 1. So here in this case, if y is 0, it could be like red, right? If y is 1, then it's blue. So say we have a data point. We know the true label is red, so y is 0. If we plug in into this loss, what we will get? We will get, here is canceled out. And what's remaining is log 1 minus y test, right? And we want to minimize this loss. What we need to do is to, let's see. Is a minus sign here? Yeah, there's a minus sign here. Okay, so minus and minus sign here. So if we want to minimize minus log 1 plus y, what we need to do is okay, so we need to maximize the log, and then we need to minimize y hat. So this is equivalent to minimize y hat. Remember, y hat is the predicted value. That is, if we can minimize it to be 0, then the log will be minimal. And that's actually what we want, right? Because we know the true label is y equals 0. And now if we can achieve y hat to be 0, then we are encouraging the model to learn to say y equals 0. And similarly, we can do the analysis for y equal 1. Let's do that. So if y equal 1, then the loss function here will be, so the second term disappears because y is 1 now, and it will be minus 1 times log y hat. Now we still want to minimize the loss function here. It means we want to maximize the log, and that's equivalent to maximize y hat. Maximize y hat. We want y to be closer to 1, and we know true label is y equal 1 as well. That means that minimizing the loss will encourage the model to predict y hat to be 1, which is what we want. So any questions? Don't worry, the professor will cover it again, I think. So anyways, we have the BCE loss, means binary cross entropy loss. We use it from PyTorch as well. So everything starting with a neural network NN is what we just imported at the beginning. As a loss function, you can call it criterion or just loss, whatever. And then optimizer, we use SGD, and the input is model parameter we want to optimize. And that something has gradients, that requires gradients, and setting the learning rates. And then we iterate the number of times, so the next class is about to begin. I'll finish in 4 minutes, okay? So first of all, when you set the model to training mode, it means that everything will require gradients. And we clear previous gradient if they have. And now we can compute the forward propagation by feeding the input X into the model. Model is here, right? The binary classifier. And then squeeze it, just make sure that the shape matches. And calculate the loss function, the binary BCE, right? Binary cross entropy loss. And calculate the gradient backwards, and then update the weights by using optimizer.step, and record the loss value. This is the template, the pipeline to do the training, right? And then after that, it just plot in. If we check it, the loss over the training iteration, we'll see that it's decreasing. Now, what about the does it learn how to classify? And here's some very uh, sexy visualization about what the model learned. So the higher, I mean, if the color is more to the red side, it means it has more confidence in predicting it's a red. Otherwise, if it's more blue, it will be more confident in blue. And the white boundary here is the decision boundary where there they have equal probability there. It could be blue or red with equal probability. Okay, so finally, that's the end of the tutorial, and thank you for sitting through me today, and see you next week. Thank you.